Good morning. My name is Ra-phael Ribeiro and I will present the work developed during my master's degrees at Pontifícia Universidade Católica of Rio de Janeiro, PUC-Rio. This research is an experimental study on enhanced oil recovery in porous media using confocal microscopy. Before starting, I would like to thank SPE for the opportunity to present my work and wish you to be safe during this global difficult moment. The main focus of this work is to perform experiments to improve our understanding of some aspects of the oil recovery process. In this way, we have focused on secondary and tertiary methods. Briefly speaking, secondary oil recovery consists of the injection of water or gas to pressure the reservoir. Because of the viscosity difference and capillary effects, a large part of the oil still remains inside the reservoir after the secondary recovery. Thus, tertiary methods are used to mobilize the trapped oil. These methods comprehend different strategies, such as the injection of chemicals, particles, and the addition of heat. In this work, we analyze the effects of the injection of an aqueous suspension of microcapsules in order to create blockages in the water paths. This causes the increase of local pressure. If it is greater than the capillary pressure, it mobilizes the trapped oil. The microcapsules injection is similar to the tertiary recovery method using emulsions. When injected, emulsion droplets block the water preferential path, as shown in this picture by black arrows. Then, the additional pressure forces the new paths for the water to displace the oil, as shown by red arrows. A field test of this technique was performed by Macro-Life in the Midway Sunset Field, in California in the 70s. The result showed an increase of oil production 3 months after injecting a batch of 3,000 barrels of emulsified oil in water. After almost a year, other 30,000 barrels were injected. In the end, the oil production was 55,000 barrels higher than the expected without the emulsion injection. This last image shows an example of emulsion produced in our lab. When working with emulsion injection recovery, one of the difficulties is to control the mobility properties of the emulsion. Thus, injecting microcapsules could be an alternative to the emulsion injection. The microcapsules used in this work consist of a double emulsion produced using glass capillary device. This type of microcapsules has controlled diameter and shell thickness, as expected. This work is the continuation of Ribeiro master thesis, where he injected PDMS microcapsules in an artificial porous medium. Due to the stiffness of the microcapsules used in his work, they could not penetrate deeper into the porous media. However, even with that setback, he was able to observe a small increase in oil recovery. In our research, we have improved the visualization technique and tested a softer type of microcapsules. So, in summary, the objectives of this work are two: to improve the experimental technique by achieving three-phase simultaneous visualization and by increasing the depth of visualization, which allows the investigation of regions away from the porous device walls, and to investigate EOR, by testing the use of microcapsules injected with water to mobilize oil trapped inside the porous medium. Now we should consider the review of the experimental procedure. The experimental setup is composed by 2 syringe pumps, the porous medium, and the confocal microscope. The first step involves the oil saturation of the porous medium using syringe pump 1. Then we change the syringe in pump 1 and start injecting the aqueous phase. After the injection of 10 porous volumes, no more oil is produced. At this point, we inject the aqueous phase with the suspension of microcapsules from pump 2. It is then observed an increase of oil production after the microcapsules injection, with an extra amount of oil leaving the device. A 3D image is generated after each step using the confocal microscope. Those images are used later to evaluate the recovery efficiency. In this presentation, we will show the result obtained with the one-sided glass spheres porous medium with 425 micrometers diameter. The sintered packed porous media have a theoretical pore trough size between 180 and 207 micrometers, while the capsules used have a diameter of 104 micrometers and a shell thickness of 5 micrometers. We have also performed some experiments with different porous devices, composed by layers of spheres with different diameters. However, due to time limitation, the result of these experiments will not be shown. The microcapsules adopted were prepared using a co-flow and flow-focusing capillary device. As mentioned before, microcapsules are double emulsion, in this case, oil in water in oil. The composition of each phase can be seen in the left-hand side of this slide. At the top right-hand side, a diagram presents the concept of this capillary device. Below that, there is a video showing the microcapsules production, with controlled diameter and shell thickness. Regarding the visualization technique, we use confocal microscopy. We know that confocal microscopes are commonly used in the biological area in order to analyze 3D samples. That is not achieved with common microscopes that need a cover slip. This comic strip explains the advantages of the technique, allowing 3D visualization and even a dynamic analysis of the sample. In order to produce the 3D visualization, this equipment relies on pinhole filters, which restrict all the light from out-of-focus planes and let only the focal plane light to pass through. So, each section of the sample is acquired separately, and later reconstructed to form a 3D image. Fluorescent pigments are added to each phase of the sample and are excited by a specific laser beam, emitting in different wavelengths. The emitted light is then captured by using PMT or EBIT photodetectors. The procedure for the 3D reconstruction can be better explained with these images. First, a stack of 2D images of different focal plengths are acquired from multiple positions. Then, each stack is rebuilt in 3D separated tiles. Finally, these tiles are merged together to represent the whole sample. The aqueous phase is shown in blue, the oil phase in yellow, and the capsules in purple. It is important to note that the black areas are the glass beads, which don't emit any fluorescent when excited by the laser. This color pattern will be used through all the presentation. As mentioned before, the artificial porous media used in this work are composed by a package of glass beads, sintered in a furnace at 875 degrees Celsius. It is very important for us to match the refractive index of these beads with those of the fluids in order to minimize inner refraction and to improve the depth of visualization. The porous media are placed in a square pipe of 2 mm side. Choosing the fluids for the experiments demanded the immiscibility of the oil and aqueous phase, the matching of the refractive indices, and the proper viscosity ratio between the phases. Because the phases have the same refractive indices, the confocal technique needs the addition of fluorescent pigments to distinguish them. We have carried out a survey on fluorescent pigments, which allowed the simultaneous visualization of the oil phase, microcapsules, and aqueous phase. The final part of the work aims to develop an image processing procedure to quantify the experiments. To do so, we have used two computer programs, ImageJ, an open-source software to pre-process, segment, and post-process the image, and RIS Dragonfly, which has more resources for 3D analysis than the previous one. On the right-hand side, it is possible to see a single slice before and after the segmentation. Segmenting the image means distinguish different phases in it. Let's take a look now in the experimental result. As I mentioned previously, the first step of the experimental procedure is to oil saturate the porous device. That becomes the initial state of the system. The results are presented in single-plane images to allow easier visualization. Along with the pore device properties, the color used for each phase is shown in the top corner of the following slide as a reminder. As expected, we can observe that the higher the oil injection flow rates are, the higher the oil saturation is. Some regions, highlighted in red, show pockets filled with the aqueous phase that are displaced by higher oil flow rates. A 3D visualization is also possible, allowing the analysis of the residual aqueous phase. The images of this step also show the wetting pattern of the glass beads. After the device saturated with the oil phase, we start the aqueous phase injection. As the aqueous phase flow rate increases, the following aspects can be observed: less oil trapped in the porous medium, and a larger number of smaller and separated oil ganglia. These observations are in good agreement with the work of Yaduanandan et al. And the work of Zhao et al. Then, when no more oil is produced from the porous device, the microcapsule's injection starts at a constant flow rate. It is possible to observe interesting effects of the microcapsules in this 2D image of a single slice, away from the wall, before and after the injection. The aqueous phase preferential path is blocked by some capsules as shown in these purple circles. Also, red circles in both figures show the movement of the oil ganglion inside the porous device, as a result of the microcapsule's action. Another interesting result is observed at the exit tube. Shortly after the microcapsule's injection, it is possible to see some oil production in the naked eye. Summarizing, after running many experiments, it is possible to conclude that the microcapsules work in this artificial porous device as a method to displace additional oil that was trapped before, break oil ganglia into smaller ones, and even in ganglia that are not fully mobilized, the increase of the local pressure causes small deformations. In this work, I could improve the confocal technique to achieve a good resolution. The first image on the left-hand side shows we can visualize the details in 3D images. Also, as for the picture on the right, using 3D printed design holders, we can rotate the porous device on the microscope. That allows the visualization of both sides of the device. In this way, it is possible to reconstruct and analyze the whole sample. The visualization technique allows the manipulation of the image in order to display different aspects of the face configuration. For instance, in this example, the aqueous phase is hidden in part of the device, so it's possible to single out the oil and the microcapsules. Finally, the last part of this study is to show that it's possible to quantify the phase distribution in the porous media using 3D images, plane by plane. Some techniques are used to reduce noise, such as filters and phase subtraction. The pictures on the left show the resulting images after each step of the process. The table displays the result of one experiment where the increase in oil recovery can be clearly seen. Just minutes after the beginning of the injection of the aqueous microcapsule suspension, a sensible drop of nearly 7% in the oil phase saturation is measured. A small additional oil recovery is observed by continuing the aqueous phase injection up to 10 porous volumes. Then, what can we conclude? In this project, we have improved the technique of 3D visualization of porous media flow using the confocal microscope. We have achieved imaging the 2 mm square device in its whole depth, capturing 3 distinguished phases. We have observed that the microcapsules could penetrate the porous medium and block the aqueous phase preferential paths. This blockage has had an effect on the trapped oil displacement and mobilized part of it. So, we provide the proof of the concept that supports EOR using microcapsules. Finally, it is possible to visualize the increase of the oil recovery effect by the observation of oil passing through the exit tube. This fact is also supported by the saturation data provided by image analysis. The relevance of this work is to provide data and information for further research on microcapsules injection as a way to improve oil recovery. This work has been developed in LMMP laboratory at PUC-Rio and has counted with the support of Shell and the Brazilian National Research Council, CNPq. Thank you for your attention.